Okay, let's talk about complex numbers. And I love this topic because it's like, it looks so scary. Like, what is the word complex doing there? But really, it's very simple. It's just a different type of number than we're used to. So before we get to a complex number, I'm going to ask you something. I'm going to ask you x squared plus 1 equals 0. And I'm going to ask you to solve this equation for me. So using the quadratic formula, right? We have x is equal to minus b. So if you have, this is basically x squared plus 0x plus 1 equals 0. So you're going to have x is equal to 0 plus or minus the square root of b squared, so that's 0 squared, minus 4ac, so minus 4 times 1 times 1, so minus 4, all over 2a, so all of this divided by 2. What do we get? We get x is equal to, the 0 goes away, so we have plus or minus the square root of negative 4 divided by 2. Now, how do we do this question? Okay, so we know one thing about square roots, right? If I do square root of 55, for example, that's the same as the square root of 11 times the square root of 5, right? Because you can like take the multiplication of the square root. If you do 11 times 5, you get 55, and that's inside the square root, and you can take it out like that. So let's try that over here. So we don't know how to take the square root of a negative number, so we can instead write this as x is equal to plus or minus the square root of 4 times the square root of negative 1 divided by 2. Okay, we know the square root of 4 is 2, right? So we're going to have x is equal to plus or minus 2 times the square root of negative 1 divided by 2. Now these 2's will cancel out, and you're going to be left with x is equal to plus or minus the square root of negative 1. Well, you could have just gotten that from bringing the 1 to the other side, right? Now we have x equals plus or minus square root of negative 1. So what do we do here? Well, we can't solve this equation by the numbers that we know. So what we know so far are real numbers. So what we know so far are things called real numbers. So real numbers include everything that we know so far. So like integers, negative numbers, partial fractions, all those things are called real numbers. Now this right here, we just give it a name because we don't know what it is. Well, instead of admitting that we don't know what it is, we'll just call it an imaginary number, because why not, right? We're not going to accept defeat from numbers, so we're just going to say that's an imaginary number. So we have real numbers, so now we know this, and now we have imaginary numbers, which we see where they come from, but we don't really know what it is. Now going back to complex numbers, so what is a complex number? So a complex number is basically a real number, so real plus an imaginary number. That's it. This is a complex number. So if you have a real number plus a complex number plus an imaginary number, then you get a complex number. That's why it's complex, because it has more than one thing. It has two types of numbers now. So this is just a different type of number. Okay, so like, what does this mean? So like, let's say I gave you, for example, so complex numbers are usually denoted by the letter z, okay? Z, z, whatever you want to call it. So z, and we write it as a plus b times I. Okay, remember this I is the imaginary. And now the interesting thing is, and this might throw you off, but just try to remember, a is a real number and b is also a real number. So a complex number is a real number plus a real number times an imaginary number. And it makes sense, right? You can't just have, you could have the imaginary number on its own, but even an imaginary number is being multiplied by 1. In this case over here, for example, just I, right? I is just 1 times I. So I is equal to 1 times I. So I is an imaginary number, but then an imaginary number multiplied by a real number. So real numbers are still there. It's not like they've gone away. It's just, this is the way they're written. And it's very simple. So for example, I give you z is equal to 4 plus 6i, for example, right? Well, this is a complex number. And now you're going to understand something interesting, right? Because think about it. If I just gave you z is equal to 4, well, this is also a complex number. But you're going to be like, wait, 4 is just a real number, right? How can this be a complex number? But it is a complex number because this is basically 4 plus 0 times I. And look, this is a real number, 4 is a real number, 0 is a real number, right? We know 0 is a real number, and I is an imaginary number. So look, it meets the criteria that we put out over here. This is why I wrote it out like this. We have A as a real number, B as a real number, and then I as imaginary. And that means that any number, so any real number is also in fact complex number, is also complex. So we've been working with complex numbers our whole life just without knowing it. So any real number is complex, but any complex number is not real. So if I gave you z is equal to 2i, well, this is complex, right? Is it complex? Let's check. Does it meet our criteria? Well, just 2i is the same as 0 plus 2i. Well, we have real, and we have imaginary. Okay, so far so good. But it's not a real number. So because 2i, well, as soon as you put the I there, it becomes imaginary, right? You're multiplying by something that doesn't really exist. So now this becomes an imaginary. So this is a complex number, but it's not a real number. So not all complex numbers are real numbers. So now look what we have done. So we have basically expanded our horizons of knowledge, because like now we know that we have a different type of number, and those are called complex numbers, and we've been working with them our whole life. In fact, we've been working as a subset of them. So not all complex numbers are real. And this is not something that you really need to understand right now. You just need to like know that this is true. Not all complex numbers are real. Because we know what a real number is. A real number is just what we're used to. But now we've defined a complex number to be in this form, a plus bi. And we saw that any real number, so just 4 for example, well, that's 4 plus 0i, so it has a real and an imaginary part, so it becomes complex. But any complex number, so just like 2i for example, well, that's not a real number, and we know that because we know that that's not a real number. We just know 2, and when you put an I, we didn't know what that was before, so it's not a real number. Okay, enough talk about that. Let's start working with them now. So how do we actually use these things? So let's say I gave you, so I'm going to give you z1 is equal to, let's say I give you I plus 2, for example. So you can write it as 2 plus I plus 2 is the same thing, it doesn't really matter. And then I give you z2 is equal to 3i minus 6, for example. And I say do these, so I say do z1 plus z2, do z1 minus z2, do z1 times z2, and then do z1 divided by z2. So what would we get in all these cases? Well, let's start with the basics, right? So z1 plus z2. Well, as you would assume, or as you would expect, you just add the real parts together and you add the imaginary parts together. So you do I plus 3i, so you would have 4i. And then you do 2 minus 6, so you would have minus 4. So you can write this as 4i minus 1 if you want. It's up to you if you want to factorize, it doesn't really matter. But yeah, that's how you do it. Imagine I was like x, for example. That's literally how you're treating it. So this is what you get. And of course, if you want to write it in our original form as real plus a real imaginary, then that would be minus 4 plus 4i. This is the exact same thing. Let's do z1 minus z2. What do we get? Okay, we have I plus 2 minus 3i minus 6. So I'm going to write it as I plus 2 minus 3i minus 6. And again, we do the imaginary minus the imaginary, so you get negative 2i. And then we do the real minus the real. So we do 2 minus minus 6, and we get plus 8. So we end up getting 8 minus 2i, which is equal to 2, 4 minus 2i. If you want to factorize, it's up to you. But yeah, so that's how you add and subtract complex numbers. Very simple so far. It's literally basic algebra. It's like imagine I was an x and then you work with that. Now something interesting, z1 times z2. So how do you do that? Well, you have I plus 2 times 3i minus 6. Okay, what do you do now? Well, you do I times, you just do like the normal multiplication. Again, we use FOIL because we know, imagine this was an x instead, right? You just multiply these brackets out. So you do I times 3i, so you would have 3i squared. Then you do 2 plus 2 times 3i, so plus 6i. Then you would have I minus 6, you would have minus 6i. And then you'd have 2 times minus 6 is minus 12. So you have that, which is equal to, well, this will cancel out with this, right? 6i minus 6i is just 0. Now you have 3i squared minus 12. But we know what I squared is, right? I squared is equal to negative 1. This is the definition of I squared. Right here. Because look, we let x equal I. So this right here, x is the square root of negative 1, is the imaginary I right here. So if x is equal to I, which is equal to the square root of negative 1, then wait, I squared is just equal to negative 1, right? That's what I is. Well, then we end up getting 3 times negative 1 minus 12, which is equal to negative 15. So we ended up getting another complex number when you multiply two complex numbers, and that's what you would expect. No, this is a real number, but it's also a complex number, because remember, any real number is a complex number. Okay, that's good. Now I want you to think about why we ended up getting just a real number. What if I gave you, for example, I plus 3 minus, I give you I plus 3 times, let's say, 2i minus 1. Would I still only end up getting a real number? Let's try. So I'd have 2i squared plus 6i minus I minus 3. What do we get? We get 2 times I squared is 2 times negative 1. So we have negative 2 plus 6i minus 1. Oh, it's minus I, sorry. This should be minus I. We have 2i squared plus 6i minus I minus 3, which is equal to negative 2 plus 6i minus I, so plus 5i. And then minus 3. So we end up getting negative 5 plus 5i. So here, wait, hold on. Here we get a complex number, not just a real number. We get an actual complex number. This is not a real number. This is a real number and complex. This is complex, but not real. So what happened here? So why did we end up getting a complex number here, but we ended up getting a real number here? Why is this also not real? So think about it. I gave you 3i minus 6 and I gave you I plus 2. That is actually 3 times I minus 2 times I plus 2. Because this can be factorized, right? You can factorize this as 3 times I minus 2. So now this is basically 3 times I plus 2 and I minus 2. Now what do we get? Look, this is the difference of two squares, but now we're working with complex numbers instead. So I'm going to have 3 and I'm going to have I squared plus 2i minus 2i minus 4, which is equal to 3 times, okay, I squared is negative 1. These will cancel out, and then you have minus 4. And now this is negative 15. So look what happened here. I gave you a number. I did this on purpose because I gave you this because you could factorize this and end up getting a difference of two squares. So what does this actually tell you? This tells you that, remember, from your previous algebra knowledge, you have difference of two squares, right? Remember the difference of two squares when we had a plus b times a minus b, and we ended up getting a squared minus b squared? Well, what do we have here? Now, I've written this as a difference of two squares in terms of I, so I is first. But in general, I've written this in a form that we're not really used to working with. We're used to working with this form right here, but you can change it around if you want. I just change it around because it's easier for me to work with. I've been used to that. But in general, if you have a complex number, a plus bi, times another complex number, or times it's the difference of two square, a minus bi. By the way, this is called the conjugate. So conjugate just means changing the sign around. So if it's a positive, you make it a negative. If it's a negative, you make it a positive. So these are conjugates. And this is actually going to come in useful later. I'm going to tell you something about it. So when you multiply two conjugates, what you end up getting is you get a squared plus abi, and then you have minus abi. Then you end up having minus b squared and I squared. Okay, what's happened here? So we have a squared minus, and then this goes away, so we have minus b squared times negative 1, because I squared is negative 1, and we actually end up getting a squared plus b squared this time. So remember, when you had the difference of two squares from your previous knowledge, when you did a plus b, a minus b, you ended up getting a squared minus b squared. Now we're working with complex numbers, and this I right here, because of the way it works, it ends up giving you a squared plus b squared. So for example, if I gave you 4 plus 3i, and then I gave you times 4 minus 3i, so multiplying by the conjugate. Well, before we even do any working out, we expect it to be a squared plus b squared, so we expect it to be 16 plus 9, which is equal to 25. Let's try it. So we have 4 times 4 is 16, plus 3i times 4 is plus 12i, and then plus 4 times negative 3i is negative 12i, and then plus 3i times minus 3i is negative 9i squared, which is equal to 16 minus 9, and then I squared is negative 1. So we end up getting 16 plus 9, which is 25. So look, multiplying a complex number by its conjugate actually ends up giving you a squared plus b squared. This is different from our previous knowledge of algebra where you got a squared minus b squared. Now we divide to complex numbers. So I do z1 divided by z2. So we did a lot of multiplication, we looked at conjugates, and now these conjugates will come in so useful because of the way they work. So I'm going to do I plus 2 divided by, or should we just change the numbers up? Let's just make it interesting. Let's make it interesting. Let's do I plus 2 divided by its conjugate, I minus 2. Okay, so right now we don't even understand what this means because we don't know, what does this even mean? Like, how do I even do this? forget about what it means. So right now I'm not going to show you what it means. That's because you need like diagrams for that, but I'm going to show you how to do it. So what you do is, you can't really do anything right now because of the form it's in. But what if I multiply everything by the conjugate of the denominator? So what am I saying? So I'm saying I plus 2 divided by I minus 2, right? We have that. I'm going to multiply everything by this conjugate. So I'm going to have times I plus 2, and then I'm going to have divided by I plus 2. Because look, that's basically multiplying by 1, right? I'm not changing anything. If I multiply by 1, I'm leaving it how it is. But look, this denominator now will become a real number, right? Because look, it's difference of two squares. It's I plus 2, I minus 2. It's a difference of two squares in terms of I instead of in terms of A and B. You'll see what I mean. Let's just do the thing. So we have I plus 2 times I plus 2. So we have I squared plus 2I plus 2I plus 4 divided by, and now we have I squared minus 2I plus 2I minus 4. So what do we end up getting? Well, I squared is -1, so we have -1 plus 4I plus 4. So we have 3 plus 4I divided by, and now these will cancel out and we'll be left with -1 minus 4, which is -5. And now look, now we can understand what this means, because now this is basically -3 over 5 minus 4I over 5. You can just distribute the 5 into both of these and you end up getting this. So multiplying by the conjugate actually ended up giving you what you needed. So this is our actual final answer. So I plus 2 divided by I minus 2 gives you -3 over 5 minus 4I over 5. Now this has some interesting properties, but for that we need Argand diagrams and all of that, and that's a separate thing. So now, what I really want to look at is this. The fundamental theorem of algebra. So I'm going to write this. Fundamental theorem. It has a very fancy name, but like it doesn't really mean anything. It's really what we know already. We already know what to do with it. Okay, so fundamental theorem of algebra. I'm going to underline it because it's special name. Okay. So what is this? So this says basically, let's say I give you an equation like this. So let's say I give you a n x to the power n plus a n minus 1 x to the power n minus 1 plus da, da, da. So all this is saying is if I gave you an equation with the power n, right? So let's say I gave you 55 x to the power 6 plus 32 x to the power 5 plus 4 x to the power 4 plus everything, and then here plus everything, and then plus just a constant, so x to the power 0 and then a0 is equal to 0. So let's say I gave you plus something 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 and then plus 5 equals 0. So I've just given you a very big equation. So this is the formula we're writing it. This is just what it actually means. So these are just constants right here. Constants, constants, constants. It's a coefficients. And then this is the term that we're interested in. So this is the biggest term, right? X to the n. So our biggest term here is 6. So this means that there are going to be n roots of that equation. N roots of equation. So this means in our case that we're going to have 6 roots for this equation. We don't know what the roots are. It's not telling us how to find the roots. It's not telling us what the roots are. It's just telling you you're going to have 6 roots no matter what you do. So 6 roots of equation. And now this is why we didn't accept defeat over here. We didn't accept saying that, oh, we don't know how to solve this equation, because we know x squared plus 1 equals 0 is going to have 2 roots, because look, the power of 2 right here. That means we need 2 roots. So we need it to have 2 roots. And that's why we had to invent this imaginary number to give us the 2 roots. So in this case, the roots would be plus or minus I. So that would be the 2 roots. And plus or minus I is a complex number, right? So for example, plus or minus I, so like this is 0 plus I, and then this is 0 minus I. Those are the 2 roots of the equation. X squared plus 1 equals 0. 2 roots of equation. X squared plus 1 equals 0. So look, even this equation here had 2 roots, and the biggest power here was 2. So this means that any equation is going to have, so if it has 6 roots, that means they're going to be, if this is an equation of power 6, that means it's going to have 6 roots. So one more important thing before we do some worked examples. If you have a root, and we're going to see it in the example question, but once you have one root, so let's say I gave you one root, right? Let's say I gave you a root of this equation is 1 plus 2i. Okay, I told you 1 plus 2i is the solution to this equation right here, for example. Then you already know the other root. The other root is going to be 1 minus 2i. which is the conjugate of 1 plus 2i. So this is the second root. So look, this is very, very important, and you can see this works here as well. You had 0 plus I and you have 0 minus I as the conjugate roots. And you can kind of see from the quadratic formula that you would end up getting conjugate roots, because look, you're going to have the plus or minus there, which is going to end up giving you a plus or minus of the imaginary part. So this is very important. You need to understand that if you have one root of an equation which is complex, you already have the other root, which is just going to be its conjugate. So just remember this, because it's going to be useful in this question that we're about to do, okay? So verify that minus 1 plus root 2i is a root of the equation. All of this is equal to 0. I'm going to say all of that. Okay, so what do? Well, we just need to put this number, this complex number, back into this, and hopefully it works. So let's try it. So we have minus 1 plus root 2i. So first of all, we need to square it, right? So we're going to have minus 1 plus root 2i. And what's that going to give us? That's going to give us 1. And then minus root 2i, so minus 2 root 2i. And then plus 2 times I squared, so minus 2. Which is just minus 1 minus 2 root 2i. Okay, so far so good. That's not that bad. So this is z squared, right? Because we just squared this right here. This is z and this is z squared. Okay, now we need to square this as well. So we need minus 1 minus 2 root 2i times minus 1 minus 2 root 2i. And now what will we get? Okay, so we have minus 1 times 1 is 1. We have minus 2 root 2 times negative 1, so that's plus 2 root 2, and we have 2 of those. So we have plus 4 root 2i. And then we have negative 2 root 2 times negative 2 root 2, so we have plus 8, and then we have I squared, which is negative, which is negative 1, so we have minus 8, which ends up giving negative 7 plus 4 root 2i. If that didn't make sense, or that went too fast for that, then just try this out by yourself on paper and pen, and it will make sense to you. It's just FOIL. Okay, so we have this is z to the power 4. And now we have everything that we need to just put it back into this equation, and let's see if it works. So we have minus 7 plus 4 root 2i plus 3 times this. So we have minus 3 minus 6 root 2i. I just multiplied everything by 3, so I did minus 1 times 3, and I did minus 2 root 2 times 3. Minus 2 root 2i times 3. And then I have plus 2 of these, so I have plus, so I'll actually have negative 2 plus 2 root 2i. Because I just multiplied everything here by 2. And then I have plus 12 equals 0. So let's see. We have minus 7, minus 3, minus 2, plus 12. So that's minus 12 plus 12. And then for the i's, I have 4 root 2 minus 6 root 2 plus 2 root 2, which is minus 2 root 2i plus 2 root 2i. And look, this goes to 0. This goes to 0. So you end up getting 0. And that's it. So we have verified that one of the roots of this equation is going to be minus 1 plus root 2i. And that was an easy question. That was just simple. Now find the other roots of this equation. So what do we know? So we know there are going to be 4 roots. Because by the fundamental theorem of algebra, there has to be 4 roots. We know there are 4 roots. So we need to remember this. We have 1 given to us. We have 1. But actually, since we have 1 root given, remember, the conjugate is another root. So actually, we have minus 1 plus root 2i. And we also have minus 1 minus root 2i. So we actually have 2 roots. So we have 2. Instead of just 1, we have 2 roots already. So now we need to find 2 other roots. And we already know if those are complex, they're going to be conjugates. If they're real, then we don't know if they're not going to be conjugates. It's just the way it is. We have 2 roots given to us. Now what can we do? Okay, so we know the root of the equation looks like this, right? So if I did x minus a, x minus b is equal to 0, then I know a and b are the roots, right? This is just simple knowledge from basic algebra and pre-calc, right? Quadratic equations, when you factorize it like this, you know that a and b are the roots. But in our case, we have something to the power 4. Well, we know 2 of the roots, right? So that means z minus this thing right here, z minus 1 plus root 2i, times z minus, and then negative 1 minus root 2i. And then we have z squared plus something with z, so plus kz plus c plus a constant is equal to 0. Now I've just factorized this equation, right? It's a power 4 equation. I know I have z squared and z squared, so I'll have z squared over here. I have z and z, so I'm going to have z squared. Then I need another z squared to make it z to the power 4. I'm going to have a kz, and I'm going to have a constant c. We need to find k and c basically, and then solve this equation. That's what we need to do. Well, let's see what happens here, because this is looking very messy right now. So let's clean this up over here. So I'm going to forget about all this for now. I'm just going to write it. I'm going to write this out better. So we have z plus 1 minus root 2i. This is plus 1 times z plus 1 plus root 2i. I'm just going to multiply this out for now, and we're going to forget about all this. So what do I have? Well, I have z squared plus z plus root 2zi. Sorry, my 2's look like, a lot like the z, is just the way it is. So we have that, and then we have plus z again, then we have plus 1, and then we have plus root 2i, and then we have minus root 2 zi, and then we have minus root 2i, and then we have minus root 2i times root 2i, so that's minus 2i squared, so that's plus 2. Okay, and what's this equal to? Well, this is equal to z squared, and I have a z and a z here, so I have plus 2z, and now look, this one and this one will cancel out, so we're not gonna be left anything over there. So I have done this, I've done this, I've done this, and now I have plus root 2i minus root 2i, so that's also gonna cancel out, and now I'm gonna have a plus 1 and a plus 2, so that's plus 3. So now look, I've gotten back to the quadratic equation that we started with. So I have z squared plus 2z plus 3. So look, I have a z squared plus 2z plus 3, so now I need to multiply it by z squared plus something with a z, and then plus something to give me our original equation right here, which is z to the power 4 plus all of that. Okay, well, I know I'm gonna need to have a 4 over here, right? Obviously, because the only way to get the constant of 12 is to do 3 times 4. So that's gonna be very simple. Now I just need to find the coefficient of z. So I need something right here. Well, I have a 3z squared. So do I want to get rid of the 3z squared? No, we want to keep it. Okay. We want to get rid of the z cubed though. So if I have 2z cubed, then I need to get rid of the 2z cubed. So I would just multiply this by a minus 2, because then this minus 2 times z squared minus 2z times z squared will be minus 2z cubed. So that would cancel out. So I'm left with z squared minus 2z plus 4. And you can multiply these out and you will see that we're good. Okay. Now what do I do? Well, now we have this equation right here, and we know this all is equal to 0. So we already solved this equation. This was done, because by solving this equation is actually how we got our original 2 roots. Now we need to solve this equation. So what do we have? We have z is equal to 2 plus or minus the square root of 4 minus 16 all over 2. We have z, this is just the quadratic formula, right? Z is equal to minus b, so 2 plus or minus the square root of b squared, so 4 minus 4ac minus 16 divided by 2a, which is 2. So we have z is equal to 2 plus or minus the square root of negative 12 divided by 2. Now once again, remember what we did at the very beginning of this long video with this negative square root. We did negative 1 times the square root of the positive version. So we did z is equal to 2 plus or minus the square root of negative 1 square root of positive 12 divided by 2. Well, this is the definition of I, right? So we have z is equal to 2 plus or minus I. Now the square root of 12 is the same as the square root of 4 times square root of 3, right? Square root of 4, square root of 3. And the square root of 4 is equal to 2. So we have 2 times the square root of 3. So we have 2 plus or minus I times 2 square root of 3 divided by 2. And all these 2's will cancel out as like a factor. So this will cancel out, this will cancel out, this will cancel out. And we'll be left with 1 plus or minus I square root 3. And look, again we get conjugate answers. We get z is equal to 1 plus root 3i. And we get z is equal to 1 minus root 3i. And these are the other 2 roots. So now we have 4 roots. And there are no more equations, right? Because, I mean, there are no more roots, because the highest power here was a 4, and we ended up getting 4 roots. We got 2 pairs of conjugate roots. So we were given 1 root, just given 1 root of these 4, and that's a complex root. And then we saw, okay, once we factorize it in a certain way, knowing what we already know, we can end up getting the other two roots by just using the quadratic formula and then knowing that, oh, it's going to be conjugate complex roots. And well, even if you didn't know they were going to be conjugates, well, look, this is a conjugate of this one, and you can try prove it to yourself why we always end up getting conjugate roots. That's up to you to do. So yeah, I hope you enjoyed this long video. I hope it made sense to you. If it didn't, let me know what didn't make sense to you and I can try to answer your questions. And yeah, this is the important fundamental theorem of algebra. Hopefully you learned something in this video. Hopefully you learned about complex numbers. And yeah, like this video if you liked it. Comment, share, subscribe, and yeah, let me know what else you want to see in future videos.